This basic drive technique has become known as synchro drive. The wheels of the K2A are controlled by a set of concentric shafts and gears. The outer shafts carry the steering forces from a single of the foot assemblies into the turret mount. Likewise, a single drive motor powers the inner drive shafts to turn each of the wheels. This configuration provides optimal maneuverability and traction for a wheeled vehicle. The K2A platform was first combined with support software in empty upper modules to form the SRV, or Standard Research Vehicle. The SRV has been very popular with both academic and industrial researchers. NASA, for example, is using Cybermation SRVs in its space station research. But the K2A was designed to do hard, repetitive work as well, so efforts were next turned to developing the software and subsystems required to do these real jobs. In the years that followed, Cybermation developed a wide variety of subsystems for navigation, obstacle detection, communications, and material handling. Today, the company offers completely integrated vehicles, such as this material handling robot. This vehicle is being trained by simply walking it through a route. The programs thus developed can be edited and stored offline and then transmitted to the vehicle for execution. The programming language of the vehicle is simple but flexible and can be learned in a matter of hours. This vehicle has been programmed to pick up an empty box from a dock and take it into another room and then return it to the dock. Between docking points, the vehicle uses the accurate dead reckoning capability of the K2A platform to stay on the proper path. Since paths are defined in memory, the switching and control problems inherent in wire following systems are greatly reduced. Interaction with personnel can be programmed to occur in a variety of ways, including timed waits, switch activations, or on the sensing of presence. Docking is accomplished by optical communications with fixed docking transponders. Before proceeding into a dock, a vehicle must request permission to dock and wait for clearance from equipment at the dock. At the dock, these communications appear as simple on-off signals. 7 additional binary signals are also available for exchanging information with the dock. The vehicle uses the guide beam of the dock to correct any accumulated error in its position and direction. When the vehicle is finished docking, the optical link may be used to exchange high-speed data with a remote host computer, and thus a new path program may be downloaded. To prevent the K2A from striking unexpected obstacles, Cybermation developed the CA01 ultrasonic collision avoidance system. Unlike conventional narrow beam systems, the CA01 illuminates the entire volume in front of the vehicle and can thus detect a much wider range of threats. The use of digital and analog signal processing allows the system to operate in the presence of high ambient noise from sources such as compressed air leaks, steam lines, and laser cutting equipment. Multiple CA01 equipped vehicles may operate in the same area without significant interference. Relatively small objects, such as this electrical cable, may be detected anywhere within the volume of coverage. When an obstacle is detected, the vehicle calculates the deceleration rate that will bring it to a smooth stop at a safe distance from the object. The vehicle will also slow down automatically if it passes close to an object. These two features greatly enhance safety when the vehicle is operated around personnel and other vehicles. The CA01 can also detect a change in surface texture and reduce the vehicle's speed automatically when negotiating uneven surfaces. When a smooth surface is again detected, the vehicle speeds back up. The demure appearance of these vehicles belies their strength and ruggedness. K2A-based vehicles can easily climb ramps that would be far too steep for conventional vehicles. In this case, the vehicle's load is carried in front to enhance stability. The K2A may also be equipped for towing operations. The tractive force of the K2A easily exceeds that of any conventional towing tractor in its weight range. Fully equipped vehicles can operate for periods in excess of 8 hours without recharging, and provisions have been made for automatic recharging on an opportunity basis. Recharge times with the BC01 battery charger run from 1/8 to 1/6 of the running time. And Cybermation also offers the BC01 battery charger with a manual interconnect. For continuous monitoring and teleoperation, Cybermation offers the FDX01 full duplex radio modem. And all Cybermation hardware and software is designed to permit rapid fault isolation and correction and fast, easy accessibility. Is no longer developmental. Such systems are available and proven. But at Cybermation, innovation is an unending process. So, if you have an application for our products, or would simply like to become more closely involved with this exciting new industry, write us at 5457 JAE Valley Road, Roanoke, Virginia, 24014, or call us at 703-982.
The Tracking and Communications Division at the Johnson Space Center, in cooperation with McDonnell Douglas Astronautics Company, is presently developing a robotic tracking system. The proposed system will have many applications in both space and industry. Upon its delivery to JSC in July 1986, the system was only capable of manually acquiring a single target. The system has since evolved to a more sophisticated level. Presently, it is able to recognize the characteristics of various targets, lock on to any one of them as specified, and track it automatically. Let's examine the system in its current stage of development and demonstrate its capabilities. An engineering model of the tracking system is housed in the turret above this Cybermation mobile platform. Here, video signals routed from the camera are digitized and processed by a special-purpose microprocessor. This microprocessor, developed by McDonnell Douglas, provides both target identification and guidance commands used to control the movement of the host vehicle. This information is displayed as numerical data on the video monitor, along with the scene viewed by the television camera. This CCD camera, mounted on top of the turret, serves as a system sensor. Currently, the engineering model must be initialized from an external file each time it is powered up. Part of this initializing procedure includes loading the descriptive parameters for specific objects displayed at a second external terminal. The system will accommodate identification parameters for up to 12 individual targets. Of these 12, 4 are currently in use. 3 are specific targets: an EVA torque wrench, an astronaut, and a payload docking target. A 4th universal target is also loaded. Plans to modify the system include the addition of E-squared proms. These integrated circuits will store the necessary information during power down to eliminate this initializing procedure. There are 2 modes in which the system can operate: automatic and manual. Let's watch the system in the automatic mode using the torque wrench as the selected target. Before starting the acquisition sequence, we will rotate the turret to move the target out of the camera's field of view. The Acquire button is then pressed, starting the automatic sequence and causing the camera to scan the target area. As each potential target comes into the field of view, its characteristics are compared with the parameters listed for the wrench. If they do not match, the system continues to scan. When the wrench is located, the system locks onto its center. It then aligns the camera and robot turret, bringing the target into the center of the camera's field of view. Once the maneuver is complete, the tracking system signals the robot platform to move toward the target. When the robot reaches a specified distance from the target, it stops and returns to the standby mode. The Cybermation platform can then be returned to its original starting position with the manual joystick located on the control box. It is now ready to acquire the next target. In its current stage of development, each new identification code must be entered at an external terminal. In future applications, this information will be included in the internal software. Let's repeat the process with the astronaut as the specified target. Let's watch as the system acquires and tracks the docking target. The tracking system acquires the universal target in a different manner. When the acquire button is pressed, the system locks onto the first target in the uppermost left of the processing window. Press the acquire button again, and the tracking system leaves the first target and moves to the next. The operator can sequence through the field of view until the desired target is obtained. The parameters for the universal target are more general and allow the system to acquire and track a target that has no specific identification code. The system can also acquire targets using the manual mode. While holding down the manual slew switch, use the appropriate controls to adjust the size and position of the acquisition gate around the desired target. In the manual mode, the system can move directly to an unidentified target and bypass the sequencing process. A true measure of this project's progress is its capacity to perform under more dynamic conditions. In addition to its ability to identify, acquire, and track a stationary target, it can also perform the same tasks with moving targets. For instance, this payload docking target is mounted on a second mobile platform which has been programmed to move across the floor. The acquisition and tracking procedure is repeated when the acquire button is pressed. The system's ability to perform more sophisticated maneuvers like these offer great promise for future applications in the space program. One potential application could aid an EVA astronaut in retrieving objects in space. This concept would employ a robot consisting of a manned maneuvering unit for propulsion and an advanced version of the existing tracking system. As demonstrated by this ground model, the system would scan an area identified by voice command and locate a specified object. With the aid of a ranging device, the tracking system would provide guidance information to maneuver the robot into position to grasp the object with robotic arms. Another concept under study would integrate the tracking system into the orbiter's mechanical arm. The tracking system will provide continuous position commands to the RMS, guiding the end effector toward a moving target with more efficiency. As the system is further refined, its practical application in space operations will multiply. We are continuing to upgrade the design of robotic tracking systems. Increased computing capability will enhance performance and enable systems to discriminate against more complex targets in a shorter period of time. Reduction in size and power consumption and other modifications to increase versatility all lie ahead. The future of this technology is unlimited, and we believe this robotic tracking system is only a first step toward an exciting future.
This videotape reviews research and development work on ALVIN, an autonomous mobile vehicle developed by the Robotics Technology Group at the Savannah River Lab. ALVIN stands for Autonomous Mobile Vehicle with Intelligent Navigation. The Savannah River Laboratory has been investigating semi-autonomous mobile vehicles like ALVIN for 3 years. ALVIN's technology is based upon a 3-wheel robotic transporter manufactured by Cybermation Corporation. This rugged industrial quality base has been proven reliable through demanding testing on a variety of floor surfaces. The transporter has sufficient torque to negotiate obstacles up to 4 inches in height, as well as climb ramps up to 20 degrees. SRL has added a unique turret containing work packages and sensors useful for performing operations in nuclear processes. Typical tasks include surveillance, monitoring, and pick-and-place operations. The turret is completely modular and can be easily removed for maintenance, enhancements, or replacement with another turret to perform different functions. SRL has developed a flexible, easy-to-use control environment to simplify the operation of the vehicle and to provide a powerful development system for writing specific industrial application programs. ALVIN's control environment allows the vehicle to navigate using software-generated maps. Currently, AutoCAD drafting software is used to accurately model the layout of a room. After a room layout is created, points are specified at locations that the vehicle needs to stop at or pass through. Interconnecting paths are also specified to connect the point locations. The completed map represents all the valid paths the vehicle will travel. Room navigation maps are converted by ALVIN's off-board host computer into a database which can be used by the vehicle. ALVIN's control environment is a menu-based software tool that allows the robot to perform high-level tasks. The hierarchical architecture of the software provides a high-level task interface to the user so that complicated motions and tasks can be programmed with a few simple English commands. Although the environment was designed for high-level vehicle control, it also allows the user to obtain low-level information necessary for diagnostic purposes. The software contains a variety of modes for running the vehicle. In the semi-autonomous or interactive mode, the operator can execute any vehicle function directly. Here, the vehicle is instructed to move to a location specified on the CAD map. A navigation algorithm built into the control environment automatically determines the optimal route for the vehicle to travel. This route is optimized based on speed, route width, and distance. Within the interactive mode, an applications programmer can inspect alternate routes to fine-tune an application program. Programming the vehicle is made very easy using a high-level programming language called MRPL, written at SRL. MRPL contains approximately 50 high-level functions to allow ALVIN to perform useful operations. MRPL contains all the necessary constructs present in most high-level languages, like conditional branching and mathematical operations, along with special functions to control the vehicle. The control environment features a complete screen editor so that programs can be easily created, saved, and later modified. After a program is completed, it can be compiled and executed. The editor contains built-in error recognition, making it virtually impossible for the user to make a syntax error. The editor immediately pops up a red window with the error and the correct grammar. MRPL was written so that new commands can be quickly added as new sensors or work packages are added to the vehicle. Within a few minutes after entering a program, the vehicle can be deployed to do a useful operation. Using its jointed lift mechanism, ALVIN here is programmed to perform a material transfer application where it first drives to a pickup location, deploys the lift, and picks up the designated payload. During a path program, ALVIN encounters an obstacle, it automatically slows down to avoid a collision. This is accomplished using a powerful ultrasonic package developed by Cybermation. It can discriminate obstacles as fine as a quarter-inch wire without difficulty. In the event that a path is completely blocked, the navigation algorithm takes over and recomputes an alternate route to assure that the vehicle arrives at its commanded location. ALVIN navigates using dead reckoning and actually counts wheel rotations to determine its X and Y floor position. For this reason, it must periodically recalibrate its position within the room. The program environment automatically estimates how much the vehicle has slipped during path programs. When it determines that the vehicle's dead reckoning accuracy is not sufficient to assure accurate motion to the next desired location, it automatically directs the vehicle to recalibrate its position. The vehicle's ultrasonic system allows it to perform this function. Passive ultrasonic markers, mounted to a wall, enable the vehicle to pinpoint its position within approximately half an inch and correct the vehicle's heading to 1 degree. Wall following can alternately be used to allow the robot to recalibrate its heading. When critical positioning is required, such as the vehicle monitoring a piece of process equipment, an active docking scheme is used. Here, the vehicle accurately aligns its infrared transponder with one on the docking stand. It then centers itself along the center line of the dock and drives in a distance programmed by the user. The vehicle is not required to make physical contact with the dock. Docking allows the vehicle position to be corrected to within 1/8 of an inch and 1/2 degree. Assuring position orientation is not the only thing checked by the environment. A number of critical vehicle parameters are automatically checked to assure that the vehicle is operating properly. If, for instance, the battery voltage were to drop to a sufficiently low level, the environment would direct the vehicle to a charging station. In this demonstration, the robot automatically docks into a charging station and engages with a battery charger. ALVIN contains 4 integral computers to control its motor drive functions, collision avoidance sensors, docking system, and user-defined functions. An STD bus computer system was added specifically to control the application-specific functions and allows almost any type of sensory or work package to be interfaced to the robot. ALVIN uses the STD computer system to control its 3-degree of freedom lift, a radiation detector, a temperature measurement system, and a camera system with an automatic pan and tilt mount. The camera is mounted on a computer-controlled pan and tilt mechanism, which enables the robot to pre-position the camera to a defined location. A microwave TV transmitter is used to send the video information back to the operator control panel. In some applications, it's desirable to deploy the robot without any operator intervention in order to quickly respond to an emergency condition or handle routine tasks. SRL developed an expert system-based process control system that allows the robot to be controlled directly from a chemical plant process control system. SRL used a software product called G2 to develop this software. In this example, the expert system is monitoring a chemical process in real time. The expert system then begins to notice that a line temperature is increasing above its normal value.
Warning, temperature sensor 1
The expert system warns the operator of the problem and automatically dispatches the robot to make a non-contact measurement on the process line. This action verifies that a high temperature condition actually exists, not a faulty sensor value. Innovation in control system design at SRL, as well as developments in new applications turrets, is enabling autonomous vehicles to perform useful tasks in nuclear environments. This technology will reduce personnel involvement in potentially hazardous or simply mundane jobs. It will also allow vehicles to perform operations in areas which are currently inaccessible to humans.